Section 15.2 is about double integrals over general regions. So I'm calling my region here D, although I'll often call it R. I'm going to use R for something else in this particular problem. So I'm taking the double integral over region D of some function with respect to area. And I've drawn here a lovely blobular region D. Okay. Now, we're going to be learning in this section techniques for some regions that are a little bit nicer and less problematic than this. But I want to just address the way this is going to interact with our definition. Because this does seem a little bit problematic, because the definition of a double integral is that it's the limit of a double Riemann sum. And the first step in creating that double Riemann sum is to chop things up into rectangles. And the problem is, this region is not built out of rectangles. Okay? If I take a look here, whoops, I meant to make that in green. If I take a look here, this rectangle right here, some of the region is in D, but some of it's not. Okay. So if I include that rectangle, I'm including too much area, but if I omit it, I'm omitting some of D. And that can be seemingly problematic with that whole first step. Well, here's what we're going to do. We're going to let R be a nice region, a rectangular region that surrounds D and completely encloses it. Okay? Now, I can certainly chop R into a bunch of little subrectangles. And then I'm going to define f of xy, capital F, as opposed to little f. Okay? And it's going to be this. It's going to be exactly the same as my height function if xy is in D. So it's going to do exactly the same thing on D that this function is doing. And it's going to be 0 if xy is not in D. Okay. So that way, when I chop this up into little subrectangles, if there's a rectangle entirely outside of D, I don't care, because it's going to contribute absolutely nothing to my Riemann sum, because that's going to be assigned a height of 0. Okay. For all of these rectangles that include the boundary of D, some of them I'm going to pick a representative point in D, so I'm going to be getting an if my height is positive there, I'll be getting an overestimate because I'll be applying that height over a bigger region. If my height is negative, I'll be getting an underestimate. But as I chop things finer and finer and finer, those errors that I get from either including too much area or not enough area, those errors are going to shrink to 0. That will be true if f is continuous on D and the boundary of D, which is that boundary curve, isn't too complicated. Now, that's not a very precise way of saying things. That's basically my way of saying the conditions for that boundary of D are beyond the scope of the class. But it seems reasonable that if things aren't too messy over here, that if I were to integrate this function over R, that would give me what I'm looking for. And that's exactly how we define things. I would say that this integral, let's see, I'm running out of space and I've lost my eraser. Oh my goodness, having a great day. Okay, this is just the double integral over R of f of xy, dA. Now that's not a definition that we're going to be working with much, but it's one that you should be aware of as you move on, because this process of chop, approximate, add, take a limit is incredibly important. But we're going to be chopping things into little rectangles. Now eventually we'll be chopping things into polar rectangles and other sorts of shapes, but not every region that we work with can be built completely and exactly out of those shapes. And so this is just the way that we deal with that issue. Important to know that. We won't be working with it a whole lot this semester.